Hey, good morning, everyone. It's 10 o'clock, so we'll go ahead and get started. We got a little timer issue on the screen there, but thank you for joining us for this week's edition of the Long Coffee Break. My name is Chris Visconti. I'm a sales engineer on the Long Hydronics, Plumbing, and Steam team. Very excited this morning to have Jeremy Zelmer with Industrial Steam with us. He's going to be talking to us about how to correctly size your boiler feed water system. Also, please stay tuned at the end. Jeremy's going to talk to us a little bit about the upcoming American Boiler Manufacturers Association Expo at the Gaylord coming up in a couple of weeks. And of course, we'll have our long prize giveaway as well. Jeremy, please take it away.
All right. Hopefully everybody's having a good morning this morning. We're going to go through on how to size and select feed water systems, give you some general, guidelines that we use in regards to sizing the tanks, and then a little bit of beginning information on what we do for sizing pumps as well. Boiler feed water systems. How do you size and select the right feed water supply and conditioning system for your project? There are 7 steps. 1, collect the information. 2, calculate the average feed water temperature. 3, calculate the total capacity of the system. Determine the connected load. Calculate the blowdown required. And add to the makeup flow. Calculate the amount of steam required by the deaerator or feed system. Choose the number and size of boilers. Choose the type, size, and quantity of boiler feed pumps. Choose the type and size of deaerator feed tank. Size the steam and water lines to the deaerator/feed tank. To calculate the average feed water temperature, this calculation provides an estimate of the average feed water temperature of the feed water. If required, that you develop a weighted average of the temperature and percentage of flow of each of the sources of feed water. A more rigorous method would be to use the thermodynamics and the steam tables to find the heat of the liquid for each of the sources of feed water, then use the heat of the liquid for each of the actual mass flow rates to determine the actual energy contained in each flow. Sum the total energy and divide it for the total mass of the feed water to determine the actual average feed water temperature. As you can see by the simple equation that we've done down here, we put together kind of what we look at, in regards to trying to figure that out. Find the total capacity required. Estimate the actual steam demand. Calculate the blowdown rate. Calculate the steam required to heat the feed water. In this step, it is determine the blowdown rate of the boilers. There are shortcut ways to eliminate the blowdown required. However, we recommend that you review the blowdown requirements with the boiler manufacturer and your water treatment supplier to arrive at an approximate level of blowdown for the boiler. No matter what, you're going to have blowdown loss. So it's just kind of one of those things, talk it over with them, make sure it does go into that calculation. So calculate the steam for feed water heat. The third step is determining the capacity of the boilers required for the project is to estimate the amount of steam which is required to heat the feed water. And this is the total boiler capacity required. 1, calculate the total energy empathy required by the feed water at the discharge temperature and maximum flow rate for the deaerator. 2, calculate the energy in each of the sources of feed water based on the condition at which they enter the deaerator. Add the energy of each of the sources of feed water together to determine the energy entering the deaerator. Calculate the amount of energy which must be added to the deaerator. Divide the total energy required in the steam by the empathy of steam at the operating pressure of the boiler to determine the total capacity of steam required. Add this capacity to a steam total requirement of the system to determine the total boiler capacity required. I know in a lot of these we're using a deaerator feed water temperature of like 225. If we were to, dumb this down and say we were just using a feed water system, you'd be looking at temperatures, in the 180 range instead. However, with, we are using the DA as typically those are more rigorous. It's more important for them based on the fact that we're pumping hot water at the deaerator. So that's why we use this in most of our examples. Steam required for feed water heat. Determine the amount of steam required to heat the feed water. Obviously, one of the reasons why we're asking you that average feed water temperature, of condensate makeup coming back is so that we can get a pretty good idea of what that how much heat we're going to need, and how many pounds per hour we're going to need out of the boiler, to heat that water up so that can go into the calculation of what we're going to need total. Calculate the total capacity, connected load. So, 34,000 connected load at the boiler. We have a 3% blowdown rate. Total heat, feed water heat needed to get us up to the temperature is 2,600. So then our total capacity jumps up to 37,000. If the blowdown and deaerator load were ignored, the load would have been undersized. So, there's the potential that we would undersize the boilers, not taking into calculations blowdown rate and what the deaerator would need, to get that feed water temperature up. Boiler feed water systems. Calculate the net boiler capacity. Example, average feed water temp of 144, which would be pretty high. You got two 500s, 200-pound design, operating at, approximately 250 pounds an hour. So then the boiler output, we have a calculation here that you're going to need, 15,940 pounds for each boiler, or 31,000 versus 34,000 load. With 100% makeup rate, that capacity would jump to 14,760. So that's why it can be very important, if we are doing 100% makeup, that we know that, and because there can be a huge difference in that steam amount. One thing I would warn against is to not just, size for the worst case scenario, because then a lot of the times you wind up getting valves that are oversized and they end up trying to hunt and they do a lot of weird things. So, oversizing too is not necessarily the right answer as well. Sizing boiler feed water pumps for the applications. Boiler feed water systems pump sizing. Choose the type, size, and quantity of the boiler feed water pumps required. Determine the number of pumps required. Calculate the evaporation rate of each boiler. Calculate the head required for each boiler. Determine if modulating feed water or on-off feed water control will be used. Determine the safety valve settings for the boilers. Will the pump satisfy ASME requirements? Choose the pump which satisfies the required conditions. Determine if recirculation is required to protect the pumps, and so which type is appropriate. Calculate the total flow. Must produce is determined by evaporation rate, connected load, blowdown load required by for feed water heat, amount of capacity required for catch-up, minimum flow required to protect the pumps. Calculate the total pump flow. The pump must produce enough flow to catch up during load swings. It varies with the type of pump. Centrifugal pumps over 200 boiler horsepower, when on-off pump is used, to figure the pump capacity, as a general rule of thumb, we will always do evaporate and double it. On vertical pumps with a modulating control, we're always going to do as a standard the evaporate times and then put a 25% safety factor on there. So in all the years that we have done this, these are what we had typically used, and for the most part, you're going to see these being used pretty widely as a standard out there in the industry. But this is a standard that we have developed without being told this is what we're going to do when we're sizing the pumps. Pump requires a minimum flow in order to cool the pump. If on-off pump control is used, it's necessary to allow for the minimum flow requirements for the pump. Modulating feed water is used, you must allow for the minimum flow requirement of the pump in order to protect against damage. So basically what we're saying between the two is that, hey, I know I need water when we're using on-off, and it's just going to run the pump when it needs it. When we got modulating control, we got to put the minimum flow in there, because there is the possibility that modulating valve could shut down to either nothing or a low enough of a flow rate that it's not enough for what the pump needs in order to maintain and keep itself cool. So minimum flow requirements applies when it is impossible for pump to operate with feed water valve control closed or below what it needs to be. So as you can see, most of the time on smaller applications, we're always going to have continuous flow figured on the pumps. with a minimum orifice line in there so that no matter what, it's always flowing back to the tank. With that, typically you're going to see on the pump, if you go to its peak efficiency, the continuous minimum flow is going to be equal to 20% of the flow at peak efficiency. So, most of the time with most of the pumps, we use a lot of the Grundfos. Grundfos has just come and said, hey, for this pump, we want this much minimum flow. And, so that's what we sized our minimum flow orifice for. Calculate the pump discharge head. The total discharge head is pressure times 2.31 divided by 0.96. The 0.96 being that we have hot 225-degree water. So we're taking out that, hey, we know that we gotta calculate and figure in for that water temperature. So based on the first selection, we have the minimum flow, we have the evaporate with the 25%, and then we have the minimum flow. So then we are ensuring that our design point for, the minimum flow rate is 63 gallons. The total pump discharge pressure is safety valve setting 175. And then as you can see, we come up to that. Whenever we're figuring any of this, on pump discharge, if we're modulating, we're going to, as a rule of thumb, put in basically a 40 PSI above the operating pressure as our design point. At a minimum to ensure that, we're always going to be able to get water into the boiler. On an on-off selection, we're going to do about 20. However, as you're going to see in this next slide, we still got to ensure that we can back this pump up. And even with not the 25% figured in and, just evaporate, that if we back the pump up on the scale, on its curve, that we can still achieve to get 3% over that safety valve point and still satisfy the ASME requirements. So as you can see, with the ASME requirements, we want to try to make sure, we're not way oversizing, but yet we still are oversized just enough that we can still achieve that requirement. 3 causes of pump problems: pressure decay in the deaerator, pumps operate too far to the right due to load swings, pumps operate too far to the right of the curve due to carryover. So as you can see on this, NPSH, especially in the deaerator, becomes very important. So, when you got that stand, where that pump operates, the reason that we're going to make that operating point, at where we get the catch up and we have the minimum flow figured, is so that we can assure that we've gotten far enough out there on the curve with enough flow that NPSH doesn't become a problem. And then, we want to make sure as well that we can still back up, but we don't want to have that pump wanting to keep going out here on this curve, that then it could get us in the requirements where we're flowing a lot more flow, but we don't have the stand height, and we start developing NPSH issue. When we say pressure decay in the deaerator, what we're talking about there is that, in the event that, we're holding 5 pounds all the time on that deaerator, we have a steam space up in there because we have 225-degree water. What that is that we need that 5 pounds of steam space, because at 225, that water wants to be boiling. But with a steam blanket on the top of it, we prevent that from happening. If that steam blanket was all of a sudden going to just disappear, then we would have an issue with pressure decay, allow room that then that water can boil and then send air bubbles down your pump suction lines and cause cavitation issues and tear pumps up. So that's what we're talking about with pressure decay. Pump problems may be caused by carryover. Causes of carryover: poor water quality. High levels of total dissolved solids lead to foaming and priming. Boiler operate at lower pressure than steam nozzle size for high velocities can cause carryover. Should pumps be oversized? Find the answer. Look at the operating point on the curve. Can the pump run off the right side of the curve if the load is removed when the boiler valve fully opens under surge loads on the boiler? If the pump is oversized, consider a valve or orifice to limit that charge on the discharge line. No, this has been kind of a quick run through, but if any further questions, please reach out to me or Chris. We'd be happy to discuss this in more detail. Before I get off the presentation today, I kind of wanted, as Chris said, I want to let everybody know about the Boiler 2024 show that is coming up here May 1st through 3rd in Denver. Some of the things that, to be at the Gaylord Rockies and Convention Center. Expo hours, scheduled events are 11 a.m. to 4 on Thursday, 10 a.m. to 2 on Friday. There's going to be a couple of boiler tours. There's going to be all of the manufacturers are going to have their boiler mobile rooms outside to be able to walk through and see. And then also Rockies is offering a boiler room tour. There's also going to be educational topics that, going on during the show as well. So if that's something that interests some of you, on these next 2 slides, there's kind of some of those confirmed educational topics, that have now are going to be there for sure. So, there's quite a bit. That's the end of my presentation. However, there is, like I said, if there's more interest in the show, the American Boiler Manufacturers has a site for the 2024 show. You can go to that website and even get more information if you so desire.
All right, thank you very much, Jeremy. As Jeremy said, if you have any questions about his presentation today or the ABMA show, please reach out to me or your long sales engineer and we can get you set up. Thank you everyone for joining us and have a good rest of your week.